Good day, everybody. So now that we are done with our introductory topic in biochemistry, as well as discussing a part on our first biomolecules, which are the carbohydrates, we will now be continuing with our topic. So for today, we will be dealing all about chirality, handedness, and molecules. So what is this all about? What do we mean when we say that um, molecules, such as carbohydrates, possess the property of chirality and handedness? So that is what you will be learning as you go through this video lesson. So our learning focus for today's class would be the following. We will be able to define the property of chirality in molecules. Next, you will be able to comprehend what the property of handedness is all about. Thirdly, we will then be able to define what isomerism is all about. Specifically, we will be dealing with stereoisomerism. And then lastly, you will be able to learn how to designate handedness using Fisher projection formulas. So again, these will be the objectives that we will be aiming to achieve at the end of this series of discussions for this topic. So without further ado, let us dive directly into our focus for this discussion. So I want you to take a look at your two hands. So take a good look at them. Now ask yourself the following questions. Are they the same or are your two hands different? When you lay them on each other, pag imo silang isapaw, you put one hand over the other, do they match one another? Can they be superimposed with one another? Now, no matter how much you try to position and rotate your hands, sa pag saon nimo siya og balhin-balhin sa iyang position, you try to rotate it as much as you can never superimpose one of your hand upon the other. Kay dili gyud na sila um, when you sapaw them upon one another, they do not match at all points in the hand. Now, they are, after all, two different hands. You cannot fit your left hand in a right hand glove, can you? Or, say, for example, if you happen to cut off your left hand, it can never be replaced by a right one and expect that you continue to live as if everything's normal, right? So, after all, um, your left hand is very different to that of your right hand. So, despite the fact that they are comprising the same, typically the same components, they're comprised of the same number of fingers, the same length. The length of your fingers in one hand is the same with that of the other. So technically, the same lang dapat sila components. However, despite that, although they typically mirror one another, they are all in all two different hands. Now, to continue, in nature, this property of handedness is also observed among many types of molecules, including carbohydrates. Now, these molecules may seem similar at one glance, but they are very different molecules. Now, what is this property of handedness, by the way, which are our first focus for this discussion? So, what is this all about? Now, an important property of molecules, including carbohydrates, our first major biomolecule, is the property of handedness. Now, molecules that possess handedness exist in two forms, a left handed form and a right handed form. So, again, what you just have to remember is that a lot of molecules, including carbohydrates, because they possess the property of handedness, they exist in two forms. Naa sila duha ka versions. You have a left-handed form and a right-handed form, the same way as we have two hands. So we have a left hand and we have a right hand. So molecules also exist in nature as or rather possessing this type of they call this character in them. They exist as having two forms, a left-handed form and a right-handed form. Now, for example, for you to be able to visualize what I'm trying to say, for example, we have here the common monosaccharide glucose. So glucose exists in two forms, one left-handed and the other right-handed. So as you can see in this image right here, we have the illustration for the D-glucose and L-glucose. One is the right-handed version, while the other is the left-handed version. Now, although they are both glucose, their left and right designation differentiates them greatly from one another. These two are different forms of glucose. One is different to that of the other. D-glucose is different to L-glucose. Now you might ask, how would you determine the difference between the two versions of a certain type of carbohydrate? For example, again in this case, glucose. So later, as we go on along our discussion, there is a very simple way, a very simple um, condition that you have to follow on how to determine whether that particular molecule is the left-handed version or the right-handed version. Now, in one glance, they may seem like similar molecules. After all, they're both glucose molecules, right? But upon closer look, take a closer look at the structure of the D-glucose and L-glucose. You can see that they are actually different from one another. Now, when you take a closer look, you can see that the two can never be superimposed upon each other the same way as our two hands, right? Now, although they literally have the same number and type of components, the arrangement or the configuration of these components in space vary among the two glucose molecules. If you can observe the arrangement of the H and OH among the two glucose molecules, makita ninyo nga nag-differ sila in the configuration of the H and OH components, right? If you take a closer look, you can see that they actually mirror one another. There are two mirror images which cannot be superimposed upon each other, therefore making them two different types of glucose molecules. So that is what I'm just trying to say, or I'm just trying to explain with the property of handedness. Technically, what you just have to remember is that um, a lot of molecules in nature, especially our focus for our discussion, the carbohydrates exist having this property, the property of handedness, making them exist in two different forms, two different molecules. Now, question, does this make the two different from one another, or are they just the same? So I believe I have already answered this question a little earlier, kanina. So yes, these two glucose molecules are different from one another. They are not the same. Now you might ask, unsa ang manifestations atong lawas to these two types of glucose molecules? Our body actually reacts differently to these different types of glucose molecules. Thus, we can indeed say na dili ni sila similar na glucose molecules. Now, non-superimposable mirror molecules are said to be chiral molecules, while those that can be superimposed are said to be achiral molecules. Now, if you take a look at the image on the right side of the presentation, you will be able to see what I'm trying to say just now. So, technically, non-superimposable mirror molecules. Say for example, katong kini these two types of glucose molecules, the D and L glucose molecules, they are non-superimposable and they mirror each other, di ba? They are mirror images of one another. Now, because of this, glucose therefore could be considered as chiral molecule, whereas um, on the other hand, those molecules that can be able or that can be superimposed are said to be achiral molecules. Again, what you just have to remember is that when two molecules are non-superimposable mirror images of one another, then those molecules could be considered chiral. Now, moving on. Okay, I have been talking repeatedly about chirality. Now, what is this chirality all about? Now, in chemistry, what determines whether or not a molecule possesses handedness? Unsa ang condition for us to consider that a certain molecule possesses the property of handedness? Now, what determines whether or not a molecule is chiral? Diba? Because handedness, when a molecule possesses the property of handedness, then that molecule, therefore, also possesses the property of being chiral. Chirality, the property of chirality. Now, to help you find the answer to these questions, familiarize yourself with the element on the right. We have here the element carbon. Now, carbon will be the star of the show moving forward in our discussion. So, carbon will be the basis on how we determine molecules as being chiral or achiral. Now, let's take a move on. Now, what you have to remember. Now, for organic and bioorganic compounds, the structural requirement for handedness or chirality is the presence of a carbon atom that has four different groups bonded to it in a tetrahedral orientation. This carbon atom is then referred to as the chiral center. Now, there can be more than one chiral centers in a compound as long as the condition for determining chiral centers are met. Furthermore, compounds having one or more chiral centers are said to be chiral. Now, what am I trying to say? Let's take a look at some of these examples. Okay, let's consider the compound bromochloroidomethane. Now, bromochloroidomethane is the simplest example of a chiral organic molecule. Now, being such, this molecule exists in two forms, diba? Molecules possessing chirality or handedness exists in two forms, left-handed and right-handed form. Now, because of its simple structure, it is often considered to be the prototypical chiral compound. Now, our goal right now is to identify whether or not the bromochloroidomethane is chiral or achiral. Now, going back on our consideration on how we consider molecule as chiral or achiral, again, what you just have to look for is that um, the carbon atom being considered for chirality should have four different groups attached to it. Again, dapat na upat ka different groups attached to that carbon for it to be considered chiral. Now, for this example, for bromochloroidomethane, does this satisfy the condition for a molecule to be considered chiral? What do you think? Yes or yes? Okay, so it does, right? Now, note the four different groups attached to the carbon atom. So, makita nato in the image here that this example, the bromochloroidomethane, does possess the four different groups attached to the carbon at the center, making that carbon a chiral center and making the bromochloroidomethane as a molecule, chiral molecule. Now again, note the four different groups attached to the carbon atom at the center. We have the first group would be the hydrogen at the top, bromine at one side, chlorine another side, and iodine below the carbon atom. Thus, indeed, we can say that this molecule is chiral because again, it satisfies the condition of having four different groups attached to that carbon atom. Now, if in the near future I will be giving you a test asking you to identify whether that carbon is chiral or not, you just have to look if naa ba siya upat ka different groups attached to that carbon atom being considered for chirality. Now, moving on. Now, if you take a look at bromochloroidomethane, you can see that the four different groups attached to the carbon atom, the chiral carbon atom, are all single atoms, single elements, right? We have hydrogen, chlorine, iodine, and bromine. Now, that isn't always the case. Now, the four different groups that can be bonded to a chiral center need not be just single atoms, as was the case in the previous example. Pwede siya actually dili lang single atoms of elements ang naka-attach to that carbon atom being considered for chirality. Now, in this example right here, in the chiral center containing molecule on the right, named glyceraldehyde, three of the groups are polyatomic entities. So makita nato in glyceraldehyde that three out of the four groups are not single atoms but are rather polyatomic entities. So I have boxed the four different groups that are attached to the carbon center of glyceraldehyde. So the four different groups attached to the carbon atom at the chiral center in this molecule are first hydrogen. We have an OH at the right side, CHO at the upper hand side, CH2OH at um, below or under the carbon atom. So we can see again that it is indeed true that the four different groups that can attach to the chiral carbon need not be single atoms, but it could also be polyatomic entities, like for example, again, as in the case of glyceraldehyde. Now let's take another molecule, the isopropyl alcohol, in consideration. Let's see if isopropyl alcohol can be considered chiral or achiral. Now, isopropyl alcohol is a three-carbon compound. So it is a compound possessing three carbon atoms. Let us see if any of the three carbon atoms in isopropyl alcohol is a chiral center. Again, in a compound, dili lang isa ka carbon atom ang pwede makonsider for chirality. Diba? I have read that earlier in the video. Um, two or more than one carbon atoms could be considered or could be observed whether that carbon atom is chiral or not, as in the case of isopropyl alcohol. So let us try to determine if all the three carbon atoms in isopropyl alcohol are chiral centers or not. So let's see. Let's take a look at the first carbon atom. So if you refer to the image on the screen, you can see that the first carbon atom is not chiral because the three groups shaded are identical. So if you take a look at the first carbon atom, you can see that three of the four groups attached to that carbon are all identical. They're all hydrogen atoms. Thus, the first carbon is not chiral. Now let's take a look at the second carbon atom. Still, this carbon is not chiral because the two groups shaded are still identical. CH3 on the left side, also CH3 on the other side. Now how about the third carbon atom? Let us try to determine if that carbon atom is chiral or not. Now this carbon atom is still not chiral because the three groups shaded are identical, the same way the first carbon atom. We can see that three similar hydrogen atoms are attached to the carbon atom. Thus, all three carbon atoms here does not satisfy the condition of determining or considering carbon as chiral center. Wala sila nag-possess of four different groups, thus all of them are not chiral centers, chiral carbons. Okay, now chiral centers within molecules are often denoted by a small asterisk, as you can see in the examples below. Now note the chiral centers in the following molecules. So for 2-butanol, you can see the carbon atom being denoted by an asterisk. So that is the chiral carbon for this compound. For 1-chloro, 1-iodoethane, you can also see the carbon atom being denoted by an asterisk, thus implying that that is the chiral carbon in this compound. Now for 3-methylhexane, again, the chiral carbon is being denoted by a small asterisk. Now on your own, I want you to determine why aren't the other carbon atoms not denoted by an asterisk, not considered chiral centers. Nga naman, nga kaning uban ng mga carbon atoms nga wala i-denote by an asterisk, not considered chiral centers. So I want you to determine the answer on your own. You try to look for the groups attached to those carbons and see if nasatisfy ba nila ang four different groups na condition for determining whether or not that carbon is chiral. Now we have here guidelines for identifying chiral centers. So aside from um, the baseline of having four different groups attached to that carbon atom, we have um, additional guidelines on identifying chiral centers. Now first, a carbon atom involved in a multiple bond, whether it be double or triple bond, can never be a chiral center. Again, a carbon atom nga na ay multiple bond, whether double or triple bond, can never be chiral centers since it has a fewer than four groups bonded to it. So, dira palang daan, pag ma-notice ninyo nga na ay double or triple bond, that can already tell you that kulang na siya diretso o groups bonded to it. Wala na niya na-satisfy ang upat ka groups bonded to it. Therefore, when that is the case, then that carbon atom is automatic, not chiral. Second condition or second guideline, the commonly encountered entities CH3 and CH2 in a structural formula never involve chiral centers because of the presence of two or more like hydrogen atoms, as is the case here in isopropyl alcohol, CH3, right? For the first carbon atom, you can see CH3, three identical hydrogen atoms are attached, therefore, it can never be chiral carbon. Now, third guideline, carbon atoms in a ring system, if not involved in multiple bonding, can be chiral centers. Now, such carbon atoms have four bonds, two to neighboring atoms in the ring to, and two to substituents on the ring. Chirality occurs when both one, the two substituents are different, and two, the two halves of the ring emanating from the chiral centers are different. Now let us refer to the following slide for an illustration of what I'm trying to say here for guideline number 3. Now we have here an illustration of a ring system, and let us try to determine whether this shaded carbon atom is chiral or not. Now, helpful note for this one, if the two substituents attached, again, if the two substituents attached to the carbon atom in observation and the two halves of the rings are different, then that carbon atom is chiral. Now, take a look at the first ring system. You can see that you have hydrogen as one of the groups, chlorine as the second group, but you can see that the two halves of the ring system are identical, diba? Thus, this is not chiral. This is an achiral molecule. Since again, two halves of the ring are the same. Now, second example. Second example, we can see that this is chiral molecule. Since you can observe that two halves of the rings are different. You can see that one half of the ring possesses a double bond, whereas the other does not. Third example, this is a chiral molecule because again, the two halves of the ring are the same. The same is true with that of the fourth example, achiral gihapon ni siya because again, two halves of the rings are the same. Now, to give you more exercises on how to identify whether carbon atoms are chiral or not, let's have some more examples on this. So I want you to indicate whether the circled carbon atom in each of the following molecules is chiral centers. Okay, let's try this first one. So for this one, I want you to pause the video and try to determine if the carbon atom encircled is chiral or not. Okay, so what do you think? Is that chiral or not? Okay, so solution, yes, that is a chiral center. So you can see the four different groups are being enclosed in a box. Makita ninyo ang apat ka different groups attached to that carbon atom. First group is the hydrogen atom, first one. Next is going to the left, CH3, going down, chlorine, going to the far right, CH2, CH3. So this one satisfies the condition of having four different groups attached to that carbon atom. Okay, let's have this one. How about this one? Is this carbon atom chiral or not? So again, as per the guidelines kanina, the conditions I have read kanina, a carbon atom having multiple bonds can never be chiral center. So this one, automatic, is not chiral. So no chiral center is present. The carbon atom is attached to only three groups since it is involved in a double bond. So again, automatic, this carbon atom could never be chiral carbon. Okay, how about this one? Is the carbon atom encircled in this one chiral or not? Okay, so again, for this one, no chiral center is present. Now, why is that? Now, two or more groups attached to the carbon atoms are identical. So, unsa di ay ang identical groups attached to the carbon atom being encircled here? We have CH2, CH3 on the left side, and another CH2, CH3 below the carbon atom. So I hope nakita ninyo. Thus, the two of the four groups are identical, making this carbon not chiral. Okay, how about for this one? We have here a ring system. Is the carbon atom being encircled chiral or not? Okay, so what are we going to do if this is the case? Now, for you to be able to identify whether this ring system is chiral or not, you can make some sort of a division. You divide the ring into two. Now, the chirality rules for ring carbon atoms are the same as those for acyclic carbon atoms. Now, for this particular example, a chiral center is present. The two of the groups attached to this carbon atom rather, is the hydrogen and bromine at the upper hand portion of the illustration. The other groups, the third group specifically, obtained by going clockwise around the ring, is CH2, CH2, another CH2, and a third CH2. So again, mo ang imong third na group. Your fourth group would be obtained by proceeding counterclockwise around the ring. So the fourth group would be a CH2, CH, Br, and CH2. So we can see that four different groups are attached to this carbon atom within the ring system. Again, the four different groups are the bromine at the upper hand side, the hydrogen atom directly attached to it. On the right side of the ring system, you have there your third group, CH2, CH2, CH2. And your fourth group, left side of the ring system, you have your CH2, CHBr, and CH2. Therefore, the carbon atom being considered or being observed is chiral. Now, in molecules, organic molecules may contain more than one chiral center. Dili always isa lang ang chiral center that can be present in a molecule. There could be more than one chiral centers. Now, for example, the following compound has two chiral centers. Now, the four different groups attached to each of the chiral carbons are shaded for easier identification. So makita ninyo that both the two um, Carbon atoms, being denoted by an asterisk, are all chiral centers. Now, for you to be able to identify the four different groups attached to each of the carbon atom, the groups are shaded in pink. So for the first chiral center, you have here on the left side of the illustration, makita ninyo ang four different groups. Okay? Now for the other chiral center, illustrated on the right side of the presentation, you also have there the four different groups attached to that carbon atom. Therefore, for this particular example, there are two chiral centers present for this one.